When you put on a pair of good noise-canceling headphones, it seems like the world around you goes silent. But how? Part of that answer might seem obvious. The physical design of the headphones, like these padded ear cushions and these snug-fitting ear tips, blocks some sound from reaching your ears. But that's only half the equation. The other half is done by your headphone's ability to manipulate the air in the tiny space between your headphone speakers and your eardrum. And if you stick around to the end, I'll show you how you can cancel noise the same way just using two home speakers. So today we'll break down what sound actually is and how noise-canceling headphones use the science of sound to keep your world quiet. So first, what is sound? Say you're playing the drums. Every time you hit the drum, you hear a sound. But sound in the way we think of it isn't coming from the drum. When you hit the drum head vibrates forwards and backwards. When it vibrates forward, the air particles immediately next to the drum head are also pushed forward. This causes the particles to vibrate, which in turn bump into the particles next to them and cause them to vibrate, and the chain continues. When air particles bump into each other like this, it's called compression. But this only accounts for when the drum head's in a forward motion. When it's in a backward motion, the air particles have much less pressure applied to them, allowing the particles to spread out and become less densely packed. This area of low pressure is called rarefaction. This one back and forth movement of the drum head is called a cycle. But as we know, when a drum is hit, it makes a bunch of these cycles before it stops. The amount of cycles something makes per second is called the frequency, and the frequency is measured in hertz. When those compressed and decompressed air particles finally enter our ear canals, they vibrate our eardrums, which ultimately sends signals to our brain, and our brain interprets these signals as sound. One thing to keep in mind though, is that it's not the air particles that are traveling from the source to our ears, but the pressure itself. The pressure is causing the air particles to briefly bump into each other, and that pressure travels all the way to the air particles near your eardrum, which causes it to vibrate. This is why sound waves are often demonstrated using a slinky. If you can imagine the slinky as air particles, if you push it from one end, you can see the coils compress as the pressure passes through the slinky. If you pull it, you can see the coils expand as low pressure passes through the slinky. And if you combine the movements, it will look like a sound wave. On paper, you'll usually see sound waves represented like this. For a sound that's just one simple tone, you can recognize one cycle by looking from any point on the wave to where it starts to repeat the same pattern again. The height of the wave at each point in time tells us the amount of pressure that's being applied to the particles. When the wave peaks upward at its highest pressure, that's when the air particles are most compressed. And when the wave dips down to its lowest pressure, that's where the particles are most spread apart. This constant fluctuation between low and high pressure moving through the air is called a pressure wave. But when it happens at a frequency that humans can hear, it's specifically called a sound wave. Humans can hear frequencies from around 20 hertz to 20,000 hertz. Low frequencies produce a low pitch, and high frequencies produce a high pitch. Any frequencies below what humans can hear is called infrasound, and any frequency above what humans can hear is called ultrasound. Yes, when you get a medical ultrasound, they're using high-frequency sound waves to create images of the inside of your body. So that's ultimately how sound works. But if you want to hear another example of sound working, try clicking the like and subscribe buttons. Before we get into how noise canceling works, here's a few more facts about sound that we know to be true from experience, but probably never thought about what's actually happening on a scientific level. One is that, in reality, sound travels from its source in all directions rather than just in a straight line. It travels in more of a sphere shape. But for the sake of understanding how sound works on a high level, we often simplify it in this way. The second fact is that sound travels through all solids, liquids, and gases in the same way that we demonstrated it passing through air. The only difference is, instead of air particles oscillating, it's the atoms of whatever material it's traveling through. The speed of sound depends on what it's traveling through. The last fact is that sound waves lose energy over a distance depending on what it's traveling through. We know this to be true because we know the further we are from the source of the sound, the quieter it gets. But what's happening is that, in an everyday scenario, the air particles or atoms of a material are not only bumping into each other, but other materials as well, which starts to scatter them and slow them down. Okay, now on to noise canceling. First, you should know that there's two types of noise canceling methods: passive noise cancellation and active noise cancellation. Passive noise cancellation works by physically blocking or absorbing sound waves using material like foam and insulation. It's actually what the ear cushions and the ear tips do. And while they may seem insignificant, they play a big role in blocking out mid to high frequency sounds. This is important because the other noise canceling method, active noise cancellation, works well with low frequency sounds, but not with mid to high frequency sounds. And I'll show you why in a minute. Active noise cancellation works by creating an opposite sound wave that cancels out the sound wave of the unwanted noise. On paper, if you were to copy and flip this sound wave, you would get its inverted sound wave. And if you were to play the original and the inverted sound wave at the same time from the same source, the high pressure would counteract the low pressure and cancel each other out. This means the air particles are barely moving, so they can't effectively carry the original sound wave to your ear. Imagine a ball being pushed from two sides with equal and opposite amounts of force. The ball wouldn't be able to roll. That's essentially what's happening to the air particles during active noise cancellation. So while the particles can still reach our ears, they're not moving enough to significantly vibrate our eardrums. When sound waves cancel each other out like this, it's called destructive interference. Here's what's happening inside the headphones themselves. Say you're in an office with a loud fan, so you put your headphones on noise cancellation mode to block out the noise. The sound wave that the fan produces is traveling to your ear. By the time it gets to the outside of your headphones, two things happen. The first is that some of the sound is blocked by the passive noise cancellation methods. The second is that there's at least one, but usually many microphones on the outside of your headphones, listening in for these external sounds that are entering your headphones. There's also a microphone on the inside of your headphones to determine how much of that fan noise is actually making it to your ear. Since by the time it passes through the casing of your headphones, it will likely sound lower in your ear than it does on the external microphone. In the meantime, both the inner and outer microphones are sending that data to a processor that's also inside the headphone. When the sound enters the microphones, it turns the sound waves into digital data that the processor can understand. From that data, the processor is able to generate the inverted sound wave of the original sound wave and send it back into our ears using the speakers. If you happen to be listening to music, for instance, while in noise canceling mode, your headphone speakers will actually emit a combination of two sound waves: the sound wave created by your music and the inverted sound wave of the fan. And as the original fan noise enters your headphones, it's canceled out by the inverted wave, leaving you just to hear your music. It's able to do this entire process of taking a sound wave and playing its inverse in 1 to 2 milliseconds. So the reason active noise cancellation works better for lower frequencies is because low frequencies are slower and less complex. So it's easier for the processor to predict what the inverted sound wave should be. So we know active noise canceling works between your headphone speaker and your eardrum, but now let's see it work in open space. I downloaded the desktop app Audacity, which is a free music software. In Audacity, you can invert a sound clip. So I recorded this pure tone from YouTube, duplicated it, and inverted it. I have these two speakers here, and I'm going to play the original sound from the left speaker and the inverted sound from the right speaker. Here's the original sound, and here's the inverted sound. To our ears, these two sounds seem identical, but they're actually opposites of each other. When I play them together while they're this far apart, we hear both of them. But as I push them together, you'll hear the sounds get lower and lower. In comparison, here's what it sounds like when I play just the original sound. And again, here's what it sounds like when I play the original sound and the inverted sound together. Because this works best when both sounds come from the same place, our headphones can do this much better than we can with two big speakers. But anyways, if you made it this far, comment the speaker emoji, and if you enjoyed it, check out some of my other tech explainers.